Hi everyone, I am Paulo Silva, PhD student in Computer Science of the University of Luxembourg, and today we will talk about our work on thread adaptive Byzantine fault-tolerant state machine replication. BFTSMR, state machine replication approach, helps the system to mask failures by replicating services or application state across multiple nodes. Byzantine fault-tolerant helps the system to cope with nodes with Byzantine behavior, and examples of Byzantine behavior are malicious attacks and software errors, for example. And all of that helps the system to take decisions based in consensus or a sequence of votes composed by 2f+1 correct nodes. Now I will lay down how we'll be representing the system configuration and the network configuration for the whole presentation. So here we have the F threshold, that is 2, so the system can cope with 2 faults. The N, that is the total number of replicas, and Q, that is the quorum size, so the number of replicas required to achieve consensus, to achieve agreement. And here we have the configuration, that is the S1, S2, S3, up to S7. All of these represent nodes or replicas. Previous Byzantine fault-tolerant protocols, they used to have the fixed fault threshold once, like in the designing time, and it stays the same for the whole deployment time. Previous methods also rely on some of them rely on human interaction to decide when to reconfigure the system or if they maintain the same configuration, and all of them don't stand a chance against an adversary whose strength evolves over time. So our protocol, or thread adaptive protocol, enables systems to have adaptive fault tolerance automatically or unattended, and enable them also to proactively optimize the system and the resources when less resilience is accepted according to the threat detector output, something that I will go into details in the next slides. So we are enabling the F threshold to change, and these changes that we can do in the network are either towards safety or to optimization. So going back a little bit and giving the context behind threat detectors, back in 2016, the White House published a framework where they were classifying in a color scale the difference in various threat levels, the difference in cyber attacks on various threat levels, where the level 1 was unlikely to impact public health and safety, and the level 5 could pose an imminent threat to the lives of US citizens. And in the coming years, there is development of cyber threat intelligence frameworks to better collect, disseminate, and process attacks. So one example is Cyber EU for Europe, and there are other for other countries. Also, there was in 2017 the creation of the communication standards for reporting cyber attacks. TAC-C, the description of the communication layer where the observable data of the accidents will be exchanged, and STEX, that defines how to describe this observable data. So one is the protocol, and the other the communication layer, and the other is how this information will be described to pass through the communication layer. And the increasing complexity of this, of the surveillance and mitigation of attacks of applications of nowadays, it's really increasing. So the use of these threat detectors involves lots of specialized teams. So there is a team of pen testing, a team of validation, a team of supervision, and many more. So it's many specialized teams. So before going on explaining the mechanisms that became up in our protocol, let me just explain and clarify what is the difference between an intrusion detector and a threat detector. So an intrusion detector is something that is inside the system that protects the system against an attacker that kick in either by attacking the system or by exploring a vulnerability. So the intrusion detector will act here either to remove or to tolerate this hacker, this threat. But the threat detector works in a different scale because it has many more stages, as I said, with many specialized teams. And the difference is also that in every stage, it can share the information with other applications connected to this cyber threat intelligence frameworks, and their goal is to have this response up to have real-time response really soon. So how the nodes receive the output of this threat detector? All of them receive at the same time by the wormhole connection. So they have a synchronous connection between all the nodes and the threat detector. So whenever the threat detector outputs a value, everyone receives at the same time. Another thing that I need to explain before is that in our system, to keep it exhaustion safe, we are using proactive rejuvenation. So rejuvenation is just the act of getting a fresh version of the replica, either by rebooting, by rerunning, or by running from a backup that was safe. So this is an attempt to clear the machine or either the replica from outside interference. And the fact that it's proactive rejuvenation, that we are repeating this in a time period. So for here, for example, I just put it 5 seconds, but it can change. So now let me explain the first of the two mechanisms that we came up to use in the threat adaptive protocol. So first of them is to accelerate rejuvenation, the rejuvenation period in an exhaustion safe system. So exhaustion safe system is a system that will never have its resources exhausted. So there is a period of rejuvenation that you can see here in F0, that we are that every replica waits until it repeats the process of rejuvenation again and again. So if we are able to reduce this this time interval as small as possible, as minimal as possible, as you can see in F1. So this is the first mechanism. The second mechanism is to add replicas when the system is already rejuvenating at the fastest pace. So imagine here that we are in a network distribution where we have 7 replicas. We can cope with 2 threats, and for some reason the threat detector is outputting a high chance or occurring of an attack. So our system can execute a reconfiguration without running a consensus to a safer state, where a state where the system can cope with more faulty nodes, and no consensus is needed, no human interaction is required, and no external trusted third party is required. And I will go into more details later on why they are not required here. So what if we want to use both mechanisms at the same time? So accelerating rejuvenation and adding replicas at the same time. We observe that this is true if the theorem tree that is laid down on the paper holds. So imagine that we have C0 and C0 the actual configuration, and C1 the new configuration. And the 3 conditions are that the new configuration has a bigger file threshold compared to the actual one. The rejuvenation rate changes before the moment where F increases, and replicas that are in both configurations rejuvenate at the same order. So now let's see how optimization works using threat adaptive protocol. So here we are in the network with 10 replicas, so from S1 to S10. We can cope with 3 faulty replicas, and the threat detector is showing a low chances of occurring threats. So seeing that, our system will optimize the resources, because we don't need all this resilience right now. Less resilience is accepted, so we can go for a state more optimal with better latency, where the system with just 7 replicas, where the fault threshold would be equal to 2. So we already proactively, now that we have majority of the 10 replicas, we will agree in a safe state to return whenever the system needs. So now we save that last state in a safer state pile. So the threat detector continues to show a low low chances of occurring another attack or occurring attacks. So the system can optimize even further. We can go to a configuration, the minimal configuration in this case, where we can cope just with one fault replica, and we will just save one more state on the safer state pile. Again, we decided the safe state to return when we had majority. We did experiments with reaching consensus for optimizations, and we compared our protocol with 6 other baselines. So BFT Smart with 4 replicas is the lower bound of latency. BFT Smart with 10 replicas is the upper bound of latency. Stoppable BFT is one baseline that basically has the perfect sys administrator, the one that always can prevent an attack. So always before having always before the network being attacked, this administrator will issue a reconfiguration. The group membership baseline has to reach consensus for every decision. So even during an attack, that sometimes it's not possible. ReBFT has an optimal state where it has less latency, but it only works if there's no faults in the network. And speculative, it has its gracious execution with less latency, but also if there's no faults in the network. And for the last, our protocol. If we focus on the reconfigurations, we see that our protocol is recovering. Our protocol can do the reconfiguration up to 30% faster, and we are adapting our latency from the upper bound, that is BFT Smart with 10 replicas, to the lower bound, that is BFT with 4 replicas. Now let's talk about the reconfigurations towards safety. So using previous methods, if we are in the minimal state again with just 4 replicas, and the threat detector outputs a high chances of occurring cyber threats, previous methods would have to try to reach consensus to come back to a safer or more resilient configurations. And most of the times that's not possible because they will not have a majority. Remember that the threat detector output is just a hint of what can happen the next moment. So the system could be already out of reach to reach consensus. So the configurations towards safety using the threat adaptive protocol, it's quite simple. If the threat detector outputs a high chances of occurring threat, we will just walk up in our safer state pile, picking the safer state that we already choose when we were optimizing the system. So we will just execute a reconfiguration to return to the last safer state. And here we don't need consensus because we decided already a priori. We don't. There's no human interaction required, no external trusted third party to decide for us, nothing. And imagine that here, for example, we came back to the state with 7 replicas, and for some reason the threat level is still high, showing still high chances. We just would execute the reconfiguration again and would put the system in the most resilient state possible. We did experiments on that, also comparing us with the same baselines. And if we focus on the reconfiguration, we can see that we can match our latency from the lower bound, that is BFT Smart with 4 replicas, to the upper bound, that is BFT Smart with 10 replicas. And if we compare the safety conditions for each protocol, BFT Smart, both baselines, they have fixed fault threshold, so they cannot adapt like us. Stoppable BFT is not viable because you have to have a sysadmin that always know when an attack is happening. Group membership has to reach consensus even during attack, so it's not guaranteed. ReBFT and speculative baselines, they can reach more optimal and a state with less latency, but only if there's no faults on the system. And our protocol threat adaptive is safe if the threat detector signal arrives early enough so that the theorem 3 conditions are verified. If we compare the threat adaptive, so our protocol, with the group membership baseline, that is the most viable one, we can see that we can reconfigure up to 30% faster than the group membership. The takeaway messages of this presentation are that we designed the thread adaptive protocol, a BFT SMR protocol that is able to optimize resources automatically. It proactively agrees on more resilient fallback reconfigurations and reconfigures itself to tolerate increasingly powerful adversary. The future work of this work is extending our methods to BFT protocols that make use of trusted components, like MinBFT, for example, and to consider weaker threat detector models. And that's it. Thank you.